So this is the second lesson on circle theorems, and today we're going to be looking at same segment angles and cyclic quadrilaterals. Okay, let's jump right in. So another circle theorem we have is that angles subtended at the circumference in the same segment of a circle are equal. And all that means is if you have two angles on the edge of a circle and they meet at the same points on a circle, even though the angles could be in different places, as long as they both join up to the same 2 points in a circle, the two angles will be the same. Or put simply, angles created from the same 2 points in a circle are equal. Okay? So, we can prove this because this is what we looked at last lesson. So as we can see, we said that the angle at the edge of a circle was half the size of an angle at the center of the circle, or the angle at the center was twice as big as the angle at the edge. And we can see that as our point moves around the circle, the angle on the outside, it doesn't actually change at all. So because of that, we know that when that angle is at anywhere around the circle in the segment, so not between the two angles, that's what it means by in the same segment. It doesn't mean in between the two angles. It means that the angle will always be the same, okay? So that's why if we look at this diagram on the left here, all these angles are exactly the same, and we can show that with the moving picture on the left, okay? So let's jump into some example questions. So I'm asked to find the size of the missing angle. Now I know that angle, so we're trying to find 32 and B, and I can see that I've got two angles here and they both meet at the same, they both use the same points to create themselves, okay? So that just means as simple as B is equal to 32 degrees. Job done. Okay, just like that. Let's have a look at the next one. So now we've got two missing angles, okay? But I can see that each of these angles, so angle A, I can see the 2 points. The first point, so starting at the edge of the circle, the first point is here, and the second point is there. The angle 17 that we're given, the first point, so with the edge of the circle, the first point is also on the left, and the second point is also on the right here, and it's the same for angle C as well. So that must mean that A is equal to 17 degrees, and C is also equal to 17 degrees, okay? Just like that. Now we can get slightly trickier versions of these questions, okay? So here we're given a couple of lines drawn in this shape here, and we're asked to find the size of missing angle. In this case, we're trying to find the angle Z, okay? So using the rule that we know that angles that meet at the same point at the edge of a circle will be the same as another point on the circle, okay? So I can see I got 39 degrees here, and the lines from that angle, they meet by there, and they also meet over here. Now I can also see that this angle here, its two lines also meet at this point of the circle, and they also meet at this point of the circle. That must mean that this angle here is also 39 degrees, okay? Now we're asked to find missing angle Z. So now we have to use another fact that we all know. We know that the angles in triangles always add up to 180 degrees. So angles in triangles equal 180 degrees. So therefore we know that 39 plus 25 plus angle Z has to equal 180 degrees, okay? And if you add these up, you get 64 plus Z equals 180. Z equals 180, take away 64. Therefore, Z is equal to 116 degrees. Okay, so the rule is very simple to use in practice, but we have to use that to then solve further problems. Okay, just like we've seen here. So look at one more example. So now this question looks like there's a lot more going on here, but actually, this is half of this question is a rule that we've used in the past 3 examples, and the other part of the question is something that we did last lesson. So we can see the angle 43 here is made from a point at the edge of this circle, and it also meets this point of the circle and this point of the circle. Now let's have a look at y first. We can also see that y is an angle within the circle, and it also meets at these 2 points here. Okay, if I follow the lines on y, it equals there. It equals the same 2 points. So that must mean that y is equal to 43 degrees. Okay, simple as that's that. Done. We've solved y. Y is 43 degrees. But now we need to solve for x. Now, the rule from the last lesson was angles at the center of a circle are always twice as big as the angles at the edge of the circle. So we know that x is going to be twice as big as y. And we know that y is 43. So we know that x is going to be 2 times 43 degrees. So that means that x is equal to 86 degrees. Okay? And that is your final answer for x. Okay? So these questions, the circle theorems themselves, are fairly simple to apply on their own. But as the questions get more complicated, you have to use all of the different rules together. Okay? So let's have a look at the main task. We're going to warm up first. So warm up round. So there's 4 circles here. So you need to highlight, or you need to pick which ones we can use the rule that angles in the same segment are equal. Okay? So pause the video and think to yourself, which of these circles are we able to use that rule on? Okay, so pause the video and have a think. Okay, so let's have a look at the first one here on the left. Now I can see there's the lines are touching the circle in 4 points, and it's saying that this red is equal to that red. I'm happy with that, and this blue angle is equal to this blue angle. I'm happy with that. If we have a look at the second angle, just down and to the right, again I can see the circle is being touched at 4 points, and it's saying that this red angle is equal to this red angle, and this blue angle is equal to this blue angle. I'm happy with that. That looks good to me. The third one over here, again, touching the circle at 4 points. Blue's matching blue, they're the same segment, and red is matching red, they're the same segment. I'm happy for this one. And the last one, we're touching the edge of the circle at 3 points, but the 4th point is actually in the center of the circle. It's not going to the edge of the circle, okay? So for that reason alone, this one, we can't use the rule on this diagram here, or this circle, okay? So that was the warm-up. Let's have a look at the main task. So pause the video, read the questions for part A, B, C, and D, because it asks you for slightly different things, and for E and F as well. So pause the video and have a go with these questions, okay? Best of luck. Okay, so here are the answers. Very well done if you got them all right. Had to do a bit of algebra for questions C and D, where you eventually found that for question C, 57 was equal to 3x, so you have to divide 57 by 3 to find x, and for D, you had to find 28 was equal to 4y, so you have to divide 28 by 4, okay? And question E, this is a bit of a curveball, this one. Well done if you got this right. Actually, because there's a line that goes through the center of the circle, this is a diameter line, this triangle here is actually a right angle triangle, okay? And you were to use that to find the size of angle 36 here, and then you could use the same segment rule to find the angle over there, okay? So very well done if you got that right. Okay, moving on. So now we're looking at our second circle theorem of the lesson, okay? And this one says that the sum of opposite angles in a cyclic quadrilateral is equal to 180 degrees, okay? Now this one should be fairly easy to make sense. Before we talk about it, let's have a look at the proof for this, okay? So if I've got a point, if I have an angle at the edge of a circle, I know that this angle is going to be half the size of the angle at the center of a circle. Okay, so if I had an angle here, I know that this angle is going to be half the size of this angle here. Okay, so we'll call the angle on the edge A, we'll call the angle at the center 2A. Okay, if I was to draw another point on the other side of the circle and join it up to the same 2 points I already used before, again, the angle at the edge of the circle is going to be half the size of the angle at the center of the circle. Okay, now what do we know about angles around a point? Okay, well, angles around a point equal 360 degrees. So angles around a point equals 360 degrees. Okay, so we know that 2B and 2A, both the angles together, equal the total angles around a point. Okay, so I now know that 360 degrees is equal to 2A plus 2B. Yep. Now, if I factorize this left-hand side, so 360, I'm going to factorize the left-hand side. I'm going to take out a factor of 2, okay? I could rewrite this as 360 degrees equals 2 brackets A plus B, because I've taken the common factor of 2 out. Now, if I divide both sides by 2, I will get rid of the 2 here on the right-hand side, and if I divide 360 by 2, so 360 divided by 2 is 180, and I'm left with 180 equals A plus B. So there you go. 180 degrees equals A plus B. And if you look at the new shape that we've made now, if we get rid of the lines coming from the center, we have got a four-sided shape contained within a circle, or a quadrilateral, okay? And we're saying that angles A and B, which are opposite each other, are equal to 180 degrees. So, and this works for both sides of the shape, okay? So let's show you the other side now. So again, we got one of the points on the left, we'll call that C, which is going to be half the size of the angle in the center, because the angle at the center is twice the size of the angle at the edge. On the opposite side, we're going to call it D. Angle at the edge is half the size of the angle in the center. And we follow the same thing again. Angles around a point are 360 degrees. 360 degrees equals 2C plus 2D. Factorize the right-hand side, so we've got 2 bracket C plus D. If I divide both sides by 2, I get 180 equals C plus D. Okay, so it's exactly the same thing, okay? So the summary for this rule, I'm going to get rid of this, so I should get rid of my workings out. And just to summarize this, so I'll rewrite in A and B. So A plus B equal 180 degrees, and C plus D are equal to 180 degrees, okay? And basically the rule is, in a quadrilateral contained in a circle, the opposite angles will always add up to 180 degrees, okay? So let's have a look at some questions. So, first one, we need to find the sides of the missing angles A and B, okay? So let's start looking at angle B. Well, I know that 80 plus angle B has to equal 180, because I know that opposite angles add up to 180. So I know that 180 is equal to 80 plus B. 180 take away 80 is equal to B. So 100 degrees equals B, or B is equal to 100 degrees, okay? Done, that's B done. Now for angle A, so the opposite angles have to add up to 180, so again, 180 is equal to 70 plus angle A. Therefore, 180 take away 70 is equal to angle A. Therefore, 110 degrees is angle A, or A is equal to 110 degrees, just like that. All right, let's have a look at another example. So here we go. We've got what looks like two triangles contained in a circle, but actually if we think of the whole shape, we have got a four-sided shape, or a quadrilateral, contained in the circle, okay? So we're trying to find angle E here, okay? So I know that this angle here, I'm going to call this angle X for the time being. I know that 100 degrees and x is equal to 180. So let's write this slightly differently now. So I know that x plus 100 equals 180. Therefore, x equals 180 minus 100. Therefore, x is equal to 80 degrees. Okay, so I can get rid of this, and I now can write 80 degrees in here. Okay, now I know again that angles in a triangle add up to 180 degrees. Okay, so therefore, angle E plus 80 plus 60 is equal to 180 degrees. Therefore, E plus 140 equals to 180, and I'm not going to patronize you. Something plus 140 is 180. E is equal to 40 degrees. Okay, and that's that. So again, using very simple circle theorems and just applying them in slightly complicated looking. They only look complicated at the outset, but actually it all follows through nice. So these are all rules that we've all used before. Okay, let's have a look at the last example now. So we need to find the size of the missing angle. Okay, so again, looking at this, I can see a nice quadrilateral shape here. So I know I'm going to be using my quadrilateral rule. But where am I going to start? I can't actually see any angles on the quadrilateral that are going to have to opposite angles. They're going to have to add up to 180. Or there's no angles on the quadrilateral actually. But I am told that the angle at the center, I'm told that this angle at the center is 135 degrees. And I can see that another point on the circle, it is an angle made that touches the same 2 points as that angle that makes the 135 in the center. So I'm going to call this angle X in the top here. And I know that angle X is going to be half the size of 135 degrees, okay? So X equals 135 divided by 2, okay? So X is equal to 150, 65, 67.5 degrees. That's angle X, okay? So now I know that the angle on the opposite side of the quadrilateral is 67.5 degrees. I now know that angle C plus 67.5 degrees is equal to 180. Therefore, C equals 180, take away 67.5 degrees. Therefore, C is equal to 12.5, oops, sorry, nope, 112.5 degrees. Okay, that's your final answer to question C. So now we're using all the rules that we've learned over the past couple of lessons, and we're just applying them to solve these multi-stage problems. Okay, let's have a look at the warm-up task for this second main task. So here we go, second warm-up task. Which of the circles show that opposite angles of a cyclical quadrilateral are equal? Okay, so in other words, which of these circles can we use the new rule that we've just learned? Okay, so pause the video and have a think which circles we can use the rule on. Okay, so pause the video and have a go. Okay, so let's have a look at the circle at the top left here. I can see I've got a quadrilateral and it is contained within a circle, and all 4 points of the quadrilateral are touching the circle. Okay, so that is a cyclical quadrilateral, so I can use the rule on this shape. Okay, the second shape down and to the left of it, now it is a quadrilateral and it is touching the circle at 4 points, but it isn't the 4 corners of the quadrilateral touching the circle. It's actually some point between the points that's touching the circle, and also the quadrilateral is on the outside. Okay, so unfortunately we cannot use the rule on this circle. Okay, the next one, I've got a cyclical quadrilateral that each of its 4 points are touching the edge of the circle, and it just happens to be a rectangle, and that's fine by me. So this, we can use the angles, we can use the angle rule for this circle. Okay, going down and left again to this circle, again we've got a cyclical quadrilateral, 4 points touching the circle. Yep, I'm happy we can use this rule. the rule on this circle, sorry. And then the final one, unfortunately, whilst it is touching the circle at 3 points, the one point is, it looks like it's trying to be bang on in the center, okay? But it doesn't matter because it's not, because its 4 points aren't at the edge of the circle. Cannot use this circle. We cannot use the rule on this circle, okay? So let's have a look at the main task. Here we go. So pause the video and have a go at these questions, okay? Remember just to double read the questions to make sure you're answering the right thing, okay? And best of luck. Off you go. Okay, so here are the answers. Very well done if you got them all right. So we had to use all the rules pretty much that we've used in the last, or this lesson gone, and in the last lesson as well, okay? So very well done if you got those right. Okay, let's move on to the checking questions now. So 2 checking questions. Question A, fairly straightforward, nothing too tricky with that, but question B, there's a few steps for question B, okay? So take your time with that one, okay? So pause the video and have a go at these questions, all right? Best of luck. Okay, so first of all, let's go through the answers. Let's go through question A first of all. So we're told that angle XWZ is equal to 48 degrees. So that is this angle here, and we're told that that is 48 degrees. Okay. Now, I have a isosceles triangle here. These lines going through the side of the triangle here means that these angles are the same size. Okay. So that must mean that these two angles, we'll call it angle X and angle Z. So X is equal to angle Z for a start, because they're bottom angles of an isosceles triangle, they have to be the same thing. Okay, so X equals Z. And we also know that all these angles have to add up to 180. Okay, so for now, let's just call it, instead of calling it X and Z, we're going to label them both as 2X, okay, because they're going to be the same thing. So 2X, make that a fancy X, let's do that. So 2X plus 48 degrees is equal to 180 degrees, angles in a triangle, okay? So 2X, so 180, I'm going to save a bit of space here, 180, take away 48 is 132 degrees, okay? Therefore, angle X is equal to, if we divide both sides by 2, therefore angle X is going to be equal to 66 degrees, okay? Well, that's great. We found angle X, but we're actually trying to find angle Y over here, okay? And if we look at actually what's going on here, so from point X, we can see that we're going to points W and Z, and the angle Y we're trying to find is also going to points W and Z. So therefore, we know that X is going to be equal to angle Y. And because X is 66 degrees, we know that Y is equal to 66 degrees, or 66 degrees equals Y, okay? So that's the first one. Very well done if you got that one right. Now I'm going to block this off here. We need a bit more space to answer the second question, okay? So it's a two-parter, this one, question B. So first of all, we need to show that angles DCB is equal to EAB. Okay, so we're trying to find the angle of C between points D and B and the angle of A between E and B, okay? So let's find these angles first of all. So DCB, so let's find the points DCB. Well, I got DCB, okay? So I'm told that the angle DCB actually is 83 degrees. So I know that DCB equals 83 degrees. Well, great. Now, we need to find angle EAB. So there's E, there's A, and there's B again. So we're trying to find this angle in here, okay? So first things first, how are we going to do that? Well, I can see there's a quadrilateral in this shape. If I draw it out with a red line, I can see I've got this quadrilateral here, okay? So if I can find this angle here, I'm going to call that C. I will know the size of angle A because I know that they both have to add up to 180 degrees, okay? So angles on a line have to equal to 180 degrees. So on this line E to D, I know that one angle on one side is 83 degrees. Therefore, angle C has to add to 83 to get 180. Okay, so angle C plus 83 equals 180. Therefore, angle C is equal to 97 degrees. Okay, job done. So we found that angle C is 97 degrees. 97 degrees. Now, because angle A is opposite angle C, we know that they both have to add up to 180 degrees. So, and because we now know that C is 97, A plus C equals 180. So A plus 97, 97 equals 180. That means that A is equal to 83 degrees. Okay, job done. So we've proven that DCB, which is 83 degrees, is also equal to angle A, which is 83 degrees. Okay, so DCB equals EAB. So 83 degrees equals 83 degrees. Okay, cool. That's the first part done now. Now the second part is we need to find the angle AEC. So let's get rid of our doodles here. We need to find the angle AEC. So that is A is there, E is here, and C is down there. So we're trying to find this whole angle here. Okay. Now we need to find out two smaller angles before we can do this. Okay, I'm going to label these in blue and red. So we need to find this angle here, this angle in blue, and we also need to find this angle. I know I said red. I'm going to do it in green. Okay. So the green angle, first of all, we know that the green angle, let's call that X, again, because we like X. So because it's an isosceles triangle, so we can see those two lines going through the triangle here, this is an isosceles triangle, okay? So I know that the angle E in the corner here and angle B over here are going to be the same, okay? And I know that they have to add together and to angle C to be 180 degrees, okay? Or we can write that as 2x plus C, which if we remember was 97. So 2x plus 97 equals 180 degrees. Okay, so that means that 2x is equal to 83 degrees, and that means that x is equal to 41.5 degrees. Okay, so we found one of the angles, and we need to find the same for the other angle. Okay, so for the blue angle now. So if you remember, we found that angle A was 83 degrees. Okay, so there's going to be two 83-degree angles in the top corners of this isosceles triangle. Again, it's an isosceles. You can see the two lines here. So, and all these angles, the little blue one here and these two 83s have to add up to 180. I'm going to call this little blue angle Y. Okay. So Y, sorry, not equals. Y plus 2 times 83 is equal to 180. And then 2 times 83, just to save space, is 166. So y plus 166 equals 180. Therefore, y is equal to 14 degrees. Okay. So I found the two smaller angles, but I need to add them up together to find the angle AEC. Okay. So let's do this in purple pen up here. So AEC is equal to, here's our colors. Let's do green first. X, Y. We're going to add these together to try and keep it neat in the purple pen. X plus Y. So AEC equals 41.5 plus 14. So it equals 55.5 degrees. Okay, and that's your final answer for the angle AEC. Okay, so there's a lot of steps going on there, okay? But very well done if you got that right. So good work today, guys. Very, very tricky lesson. They're not because the rules themselves are complicated, but it's just you have to do lots of there's multiple steps to these problems, and that's what makes them difficult. Okay? So very well done for sticking through it, and we'll see you next lesson. Bye now.